Hello and welcome. Happy Friday. I'm continuing my series on introductory Excel modeling through the medium of the problems from the ModelOff Financial Modeling World Championships. And today we've got something a little bit different, which is we're going to be looking at the board game Snakes and Ladders. So basically, the idea is you've been playing this game with your friend. You want to simulate uh, the game 5,000 times and see how it plays out. It's entirely a game of chance, no strategy. You start on the start square, you roll a dice, you move that number of squares forward, and if you land at the bottom of a ladder, you move up to the top of the ladder. If you land at the head of a snake, you slide down to the bottom of a snake, and you win when you get to the finish square, and you don't have to land on it exactly. So if you're at 31 and you roll a 4, that would take you past the finish, but that's fine. It still gets you there. If you roll a 5 or 6, that's no problem. But if you roll a 2, you'll hit the snake and slide back down, and then you're off again. And so for the avoidance of doubt, it kind of tells us, okay, this is how to read this. The start square is 0, the finish square is 34, and there are these ladders and these snakes. We're not given a workbook for this one. Again, they kind of got, in my opinion, a little better about that in later years, but let's just take these over here, and we'll do text split. So this is my from and my to, and these are my ladders. Let's call that type. And then same thing for the snakes. All right, paste as text. And then the easiest way to handle, or my preferred way to handle at least, this thing of, you can be on 31 and roll a 6 and that still gets you to 34, is just to add another category here, which is 35, 36, 37, 38, 39, and I guess, yeah, 39 is the highest you could. Let's just add 40 as well. Those all map you back to 34, and I'll just call those finish. So basically this will mean once we have these here, we don't have to do any sort of special treatment for the finish type. Okay, so freeze panes. I'm going to turn off my grid lines because I hate grid lines. And then let's get started. So we're modeling a two-player game. So first thing we want to do is let's have a turn number. Let's start off modeling 50 turns. So I'll do 51 starting at 0 because 0 is going to be the sort of starting position. Then I'll do P1 roll, P2 roll. And so here I guess the core of this simulation is being able to simulate a dice roll, and your friend there is going to be the ranBetween function, which gives you a random number, random integer between two integers. So ranBetween 1, 6 simulates a dice roll, and if you have modern Excel, you can use also randarray. So I want something with 50 rows for the 50 rounds, 2 columns for the 2 players, minimum is 1, maximum is 6, and true for integers, and that'll simulate the 100 dice rolls I need for this. If you don't have that, you just put ranBetween in one of these cells and then copy it and paste it to all the others. So then I want my P1 position, P2 position, and as you can see, every time I change anything here, these are all recalculating. So the whole idea of this simulation is, we'll figure out what happens with this set of dice rolls, and then we'll run it 5,000 times to figure out answers to various different questions we might want to ask. So each player starts off on the start square. And then, well, first, if there were no snakes and ladders, then player 1 position would just be that plus that. And copy down, copy across, same for everyone. But now the challenge is, if this number is somewhere in this from column, then we need to end up on this to column. So how are we going to do that? It's pretty simple. Actually, let's just make this a table so I don't have to give names or screw around with ranges. And that'll make it easy to do the lookup. So what we're going to do is take this. This H3 plus F4 is my kind of raw starting position. So I'm going to XLOOKUP that in from, returning from the to, and if it's not found, give me back that raw number. So in other words, if I roll an 11, that takes me up to a 22, but if I roll a 12 that isn't in here, that just stays as a 12. So I'll copy that down, copy it across, and copy it all the way down here. And you can see at the end, both players are all 34s, and at some point along the way, so here's player 1 finishing, and here a few turns before is player 2 finishing. Okie dokie. So then let's take a look at the questions we want to answer. We want to know average number of rolls required to finish for one player. So let's call it Q1 is how many rolls does it take to get to the finish? And that we can do as, let's see, you want to find the first 34, so we can do that with X match. So X match 34 against, not including turn 0, against this. And that's 11, and then we recalculate 7, 20, 14, da, 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 da. So as you can see, it jumps all over the place. But that's fine. That's sort of the whole idea here. Then the second question is, what's the average number of combined rolls by both players required for the game to finish? So for this, we need to figure out who wins. So I guess we'll do finish here. We'll do that as X match 34 against here. And then the same thing for the second player, the winner. And now the slight nuance here is if they both get, let's say they both get to 34 on this turn, then player 1 is the one who rolls first. So if they get there on the same turn, then player 1 wins. So we're going to say if the number of turns for player 1 is less than or equal to the number of turns for player 2, then player 1 wins. P1, otherwise P2 wins. And then total rolls. So again, think this through. If we finish up on, we finish up on whichever one of these is the smaller number. So in this case, we finish up on turn 4. So we're going to have 2 rolls for each player for every other round. And then if it's player 1, we'll have 1 roll in the last round. If it's player 2, we'll have 2 rolls in the last round. So it's basically going to be 2 times the minimum of these minus if this equals P1, then 1, otherwise 0. So that's the total number of rolls between the 2 players. So here you see we finish on turn 5, so they've each had 2 rolls. Let's find one where player 1 wins. And here we finish on turn 9. So player 1 has had 9 rolls, player 2 has only had 8 rolls, so that's your 17. All right, what's the next question? In a 2-person game, what's the probability that player 1 wins? Okay, so we already have what we need to answer that. So here's one player's rolls, here's the total number of rolls, and here's the winning player. And now, to turn this from a single simulation into a Monte Carlo simulation, i.e., i.e. 5,000 random simulations, the easiest way to do that is with a data table. So I'm just going to run. So talked about this before. The general idea for a data table is you can say, what would each of these things be if I plug this value into some driver cell? But in this case, you don't need a driver cell because it recalculates every time. So it's enough to say, what would it be if I plug these into any cell that's not being used? So I'm just going to randomly put it in here. When I'm referencing an empty cell, I like to just format it to say, don't screw around with this, don't put something in there, because that might change things. And then we can say Alt-DT for data table, and my column input cell is going to be this. So in other words, what do each of these 3 values become if I put in a 1 here, 2 here, 3 here, 4 here, all the way down to 5,000? The 1 to 5,000 doesn't change the calculation, so it's just a way of saying run it 5,000 times. And here we go. So now I'm going to take the average of these. Oh, and you see now we've got some NAs, so that's telling me that sometimes I'm X matching 34 against this, and there is no 34, which means I haven't modeled enough rounds. So let's model more rounds. And luckily we've set this up in a pretty dynamic way, so let's just go to 100 rounds for simplicity. Make that 100, and then we just need to copy these down and change these formulas to go down 50 more rows. That stays the same, that stays the same. Okay, so now these are all stay the same, so let's recalculate, try again. Much better. Okay, so now we've got 10.9. Copy this across. I'm just going to off, sorry, formulas, not data. Switch that to automatic except for data tables, so I don't want them to refresh every time. And then how many times does player 1 win? We just need to say countifs this P1 divided by rows of this. So we've got 11, 15, and 53%. So it looks like it's C, B, and B, but let's just refresh and see how much it jumps around. Still pretty close to 11, pretty close to 15, pretty close to 53. One more time, 11, 15, now we're at 52. Feeling pretty good about that being C, B, and B. So C, B, and B. All right, now for the last two questions, we're going to look at variations on this. So basically the idea is you look at this and you say, okay, player 1 has a 53% chance of winning. That's not very fair. So let's say player 2 gets to start on a different square. Given that, what are the odds of the two players winning? So now we can do a data table again, but this time instead of having one variable, which is, you know, the variable that isn't used to just say run it 5,000 times, we're going to have two variables. So we're going to vary player 2's starting position, and we're going to vary the thing that doesn't drive anything, and that's going to let us simulate the varieties. So we're interested in player 2 starting on 3, 6, 9, or 12. Sorry. Yes, that's right. Then here I just want, again, the winner, which is there. And then I want to data table that. So my row input cell is player 2's starting square, which is here. And my column input cell is this unused cell. Hit go. And then I'm just going to copy across this to figure out what percent of these player 1 wins. And then we can recalculate. It'll take a second now with the two data tables, but that's fine. Okay. So we see 52% chance of winning here, 49% here, 40%, 38%. And the question is, what gives you closest to equal odds? So I'm just going to say the absolute value of this minus 50%. In other words, how far away from 50% are we? So it looks like this one is the best. It's only a little over 0.5% off. This one's 2% off. These two are clearly very advantageous to player 2. So try it one more time. A little slow to calculate, but that's fine. We'll get there eventually. Okay, yeah, so that's definitely looking good. So that is B, which is square 6, Q4. All right, and last one is Q5. And a different way to change the odds of the game, instead of starting player 2 on a different square, you decide to give player 2 immunity to the first snake they land on. Okay, so we can still use the same player 2 role, but now we'll have to use a different player 2 position. So P2 pause, Alt, and P2 immune. Just put that as a question mark. So they start off immune. They start off on 0. That part stays the same. Then this part will mostly be the same. But now I guess we need to say, so we need to figure out if we're landing on a snake. So if you're immune, then if X lookup, yes, this plus, where's your roll here, in here, returning from here is snake, then we ignore the snake and just do that plus that. Otherwise, sorry, what was I saying? Whoa. Sorry, close bracket equals snake, not the snake as the third argument. Being very silly here. And I guess I'll just, if not found, blank, so that'll also return false. So if we would have landed on a snake, we do that. Otherwise, we do exactly what we would have done before, which is X lookup this plus this in from returning 2, if not found, this plus this. And I guess really what I want is to say if both of these first two conditions are met. So if you're immune and this lookup is equal to snake. Sorry, if you're either you're immune. Oh my god, I'm getting so confused here. If you're immune and the thing is snake, then just give me that. Otherwise, it's regular. Yes. Confusing myself, but I think that's working. And now for the immunity piece, we're going to say to stay immune, we need that is true, and basically what I want to say is that is true and we have not landed on the head of a snake. So I'm going to say countifs where from is that number and type is snake equals 0. So if you were immune and you did not land on a snake, then you stay immune. Otherwise, you stop being immune. So let's see, where do we use up the immunity? Right here, because we land on 21. 21 is a snake, so it would take us back down to 13, but it doesn't. And actually, you can see the kind of counterfactual here, because this is using the same, we're using the same dice roll for them both. So this one falls back down to 13, this one stays at 21, and everything else stays the same. So then, so I'll just do it here, put in an arrow, winner, alt. And we'll just point it to this one instead. And I think that's it. So now for Q5, we want the same formula here. We want this winner. And then we just need to expand that data table to take in one more cell. Column input is here. And recalculate. And it'll recalculate both data tables. This will take a second, but not too long. Okay, it is taking too long in my opinion, but never mind. Okay, I'm kind of not happy that it's still calculating now. Don't think it was that badly done, but anyway. All right, so 43%. Let's take a look. What are my options? 42.5, 46.5, so it's probably closest to this. Give me another decimal place. Okay, yes, it's sitting right on top of that. We'll recalculate one more time, but this time I'm going to interrupt it when it shows me down in the status bar here, which again you can't see, that it's calculating data table 1. Once it switches to data table 2, I'll just tell it to stop. And I think actually, no, I redid this one, so maybe this is now data table 2. I don't know. Let's leave it. Yeah, damn. Yes, it recalculated the wrong one. Never mind. I'm just going to trust that I have the right answer here because it is sitting right on top of it, and a range of 4% would be a pretty big range. All right, so that's how to answer the question in a nutshell. I've got, we're at about the 18-minute mark. There's a 25-minute question, so I'm going to indulge myself a little bit. This is how you do a Monte Carlo simulation. What if you wanted to know the actual answers for these questions? In other words, what is the exact probability? What is the exact number of rolls that one player will take to play this game? Well, one way that you can do that is by basically working out your probabilities of being on each square at each position. So let me show you a way to do that. Set up over here. So we've got 35 possible positions, which is everything from 0 to 34. And from each position, there are 6 possible dice rolls. So then we're going to say XLOOKUP this plus this in, did I give my table a name? I don't think so. Just called it table 1, very imaginative. Table 1, 2. Otherwise, $2 plus $A3. Copy it down, copy it across, and just shrink. Actually, do that for the whole tab. I'm just going to color code my blocks here to make it a little easier to see what's going on, because I'm going to have to add a few more. And let's do a freeze pane also and get rid of the grid lines. So this is basically saying, starting from 0, Well, if you roll a 1, that takes you to a ladder that takes you to 12. If you roll a 2, 3, 4, that takes you to 2, 3, 4. 5 takes you to a ladder to 16. 6 takes you to 6. So you can see where you go from everywhere. So now what we'd like to do is, where does that take us from each position to each position? So we're going to do sequence comma 35 comma 0. So that's my 35 possible states. And again, I'll just kind of color this block a different color. So now we can say, if I start off in position 0, what's the probability that I end up in position 0, 1, 2, 3, all the way up to 34? And it's very simple. There are 6 different possibilities. They're all equally likely. So it's just countifs. This is this block divided by 6. Gives you the probability. So you can see 0.17 and 0.1666666 chance that it's in position 2, 3, 4, 6, 12, and 16. And you can copy that down, and you get it for every different one. Interestingly, there are some here where you can end up on the same one 2 different ways, which I hadn't noticed before. So then let's get into a next block. Let's say we make this one yellow. So then that gives you the transition odds from any one position to any other position. So now on turn 0, you are 100% in position 0 and 0% chance of being anywhere else. So now, how can we figure out the probability of getting from there to each other position? Well, let's think about one position. Let's think about 12, because we know that we do have a way to end up on 12. What is the probability of getting from this configuration, this column, to 12 on the next go? Well, you could think about the probability of getting to 12 from anywhere is these numbers here. So in other words, from 0 to 12 is here, from 1 to 12 is here, from 2 to 12 is here, 3 to 12 is here, and so on down. So you basically, to figure out the odds of getting to 12, you want to multiply these numbers with these numbers. So let's just do that for 12 first. So we'll say sum product of these numbers, and I'll lock the rows with, and I'll just, to make it flexible, we'll do an index on this big block, and I want 0 for the row, meaning give me all the rows, and for the column number I want the 12. Wait, sorry, why am I? Oh, sorry, I'm in row 9. I meant to do it for row 12, but never mind. So lock that in, take the sum product. So 9, there's no chance of getting to 9, but 12, there should be, but there's not. Sad. Okay. There really should be. Okay, let's just quickly run this. Okay. Oh, sorry, beg your pardon. Yes. Confusing myself because column 1 of this is 0. So the column that has a 12 on top is actually the 13th column of the matrix. So scroll down here so we can see it. So we actually need a +1 here. Now we've worked out the probability of ending up in each different position after one roll, but we've done it in a way that only depends on, or that can basically take any combination of probabilities here. So basically now we can carry this over and over and over and over and over and over, and do this more or less as many times as we want. Let's carry it across. So after rounded up to 70 turns, you can see you're basically guaranteed to be on the finish square. So let's go back here. Yeah, so you've got like 1 in 10,000 or less chance of not being finished there. So maybe we even take it out a few more just to make sure that we're really finished. So we'll go out to the 100th turn, and now you can see, yeah, there's still vanishing probability. But anyway, so once you've done that, you can then relatively easily work out, the probability of finishing on any given turn is the probability of being finished by that turn minus the probability of being finished by the turn before. So you can fill that across. And so, for example, the expected number of rolls you can just take a sum product of this by this. In other words, the probability of finishing in 1 turn times 1, probability of finishing 2 turns times 2, probability of finishing 3 turns times 3, and so on. And then that way you can work out an exact answer. And you can see, because these odds are so small out here, it's basically not contributing anything. So you're kind of very close to an exact number. There is a lot of sort of deep math going on here. So what I've just kind of developed as though from first principles is actually a kind of well-established thing called this big orange block here is called a transition matrix. And it's used for modeling this kind of situation where you transition from a fixed set of states into other sets of states with certain probabilities. It's called Markov chains, and it kind of leads you to this very nicely. You can also do these calculations in a very neat way with matrix multiplication instead of doing this. So let me just quickly show you that for one of them. You can mmult this by, you need to take the transpose because of the way I've set it up, but by the transpose of that transition matrix. So just matrix multiply. I've done something wrong. What have I done wrong? I don't know. I'm going to pause for a second to figure out what I've done wrong. Okay, 2 seconds later, I think I have realized the dumb thing I did, which is matrix multiplication does depend on the order. So we got to put the transition matrix first. Now, yes, that's better. Now you can see it reproduces that column, and I could copy it over here. I'll copy it over for the first few just so you can see it reproduces the results, and then I'll leave the original formula here just so that they're both in the file that I upload. So that's that. I won't show you every single step of the way, but from here you can. Once you have these probabilities, it's pretty easy to figure out. The probability of player 1 winning on any given turn. Basically the probability that they win times the probability that player 2 has not won on any earlier turn. And so you can figure out, the number of rolls that way. You can obviously work out the probability. What does this look like if player 2 starts in square 3 or square 6 or square 9? The one that's a little complicated for this setup is the one where player 2 has immunity, because to figure out the immunity, you basically need to double your number of states. So in other words, you can be in position 7 and have immunity, or you can be in position 7 and not have immunity. So you actually need to develop a matrix with 70 states, which makes it a little more complicated. But it does work, and that method allows you to get exact answers for each of those questions if you want to. If I'm feeling energetic, I might even finish building out this solution in the model that I upload so you can see how to get the exact answers. But no promises. All right, that's it for today. I will be back next week with round 2, and have a good weekend.